Look up at the night sky, and what do you see? A scattering of stars, perhaps a planet or two, but beyond that serene view lies a universe teeming with enigmas so bizarre, they defy everything we think we know. Space isn't just vast, it's a stage for phenomena that leave even the brightest scientists scratching their heads. Imagine cosmic explosions that shouldn't exist, galaxies vanishing without a trace, or signals from the void that repeat like a ghostly echo. These aren't plot twists from a sci-fi novel, they're real, documented mysteries happening right now in the depths of the cosmos. And today, we're diving into 30 of the strangest, most baffling ones. What makes these phenomena so unsettling? It's not just their strangeness, it's the way they challenge the very laws of physics. Take the Great Attractor, for example, an invisible force dragging entire galaxies toward it at unimaginable speeds. Or fast radio bursts, blasts of energy so powerful they outshine entire galaxies, yet lasting just milliseconds. Then there's dark matter, an invisible web holding the universe together, yet we've never seen it directly. These aren't just curiosities, they're gaping holes in our understanding of reality itself. And with every discovery, the universe seems less like an orderly system and more like a puzzle with missing pieces. But here's the thrilling part. Each of these mysteries is a clue, a whisper from the cosmos begging us to dig deeper. Behind every unexplained signal or eerie cosmic behavior lies a story waiting to be unraveled, one that could rewrite textbooks or even reveal entirely new physics. So buckle up. Over the next 30 segments, we'll journey through black holes that shouldn't exist, stars that flicker like faulty light bulbs, and regions of space where time itself seems to warp. By the end, you'll see the night sky not as a static backdrop, but as a living, breathing enigma, one that's far stranger and far more wondrous than we ever imagined. Ready to begin? Let's go. In the summer of 1977, a radio telescope in Ohio picked up something extraordinary, a 72-second burst of radio waves so intense that astronomer Jerry Ryman scrawled, "Wow," in the margin of the data printout, giving the signal its now iconic name. What made it remarkable wasn't just its strength, but its frequency, 1,420 MHz, a silent band where cosmic noise is minimal, almost as if someone had intentionally chosen a clear channel to shout into the void. For decades, the WOW signal has haunted scientists and enthusiasts alike, standing as one of the strongest candidates for potential extraterrestrial contact, or one of the most baffling cosmic flukes. Theories about its origin range from the tantalizing to the mundane. Could it have been a transmission from an advanced civilization momentarily turning their beacon in our direction? The signal's narrow frequency band and sudden disappearance fit the profile of an intentional broadcast, yet skeptics point to natural explanations like a comet's hydrogen cloud reflecting sunlight, though later studies debunked this as no known comets were in the area at the time. Others suggest it might have been a rogue signal from a passing satellite, but the Big Ear telescope's design made that unlikely. The truth we still don't know. Despite numerous attempts to detect a repeat signal, including dedicated scans of the same patch of sky, the WOW signal remains a one-time enigma, a cosmic whisper that vanished as abruptly as it arrived. What makes this mystery endure isn't just the lack of answers, it's what the signal represents. In a universe where randomness reigns, the WOW signal feels oddly deliberate, a fleeting hint that we might not be alone. Or perhaps it's a reminder of how little we understand about the cosmos's quirks. Either way, it's a pulse of intrigue that still echoes across the decades, daring us to keep listening. Fast radio bursts are like the universe playing a cosmic game of hide and seek. Blink, and you'll miss it. Flashes of energy so intense, they release more power in milliseconds than our sun does in days. First discovered in 2007 when astronomers combing through old data spotted a burst that shouldn't have been there, FRBs have since become one of space's most tantalizing riddles. Imagine tuning a radio to static, then suddenly hearing a deafening scream that vanishes before you can even react. That's what detecting an FRB feels like for scientists. What makes these bursts so baffling isn't just their power, but their unpredictability. Most occur once and never repeat, like cosmic one-hit wonders. But then there's FRB 121102, the rebel of the group. Unlike its fleeting siblings, this one pulses over and over, sometimes in frantic clusters, other times with eerie calm. It's as if the universe is taunting us, offering clues but refusing to reveal the full picture. So what could be behind these bursts? One leading suspect: magnetars, neutron stars with magnetic fields so strong they could strip the data from your credit card from halfway across the galaxy. When these hypercharged stars snap under their own magnetic stress, they might unleash the energy equivalent of their own stellar tantrums, but not all FRBs fit this mold. Some seem too powerful, too clean, sparking wilder theories like colliding black holes or even, yes, alien megastructures beaming signals across the cosmos. Then there's the twist of their origins. Some FRBs trace back to distant galaxies, their signals warped by cosmic gas like headlights in fog. Others erupt closer to home, with one even appearing to originate inside our own Milky Way. This scattergun pattern only deepens the mystery. Are we looking at one phenomenon with many faces, or entirely different cosmic events masquerading under the same name? Every new detection peels back another layer. Recent studies found FRBs with bizarre, splitting signals, as if the burst ricocheted through an invisible maze before reaching us. Others arrive with a side of polarized light, hinting at extreme environments we've yet to imagine. With each discovery, the question shifts from what they are to how many secrets they're still hiding. One thing's certain: in a universe full of whispers, fast radio bursts are the shouts we're desperate to understand. Imagine holding a snow globe, except instead of water and glitter, it's filled with galaxies swirling in perfect equilibrium. Now shake it. The snowflakes move, but something invisible keeps them from flying apart. That something is dark matter, the universe's hidden scaffolding, an unseen force that outnumbers ordinary matter 5 to 1. We know it's there because galaxies rotate too fast to hold themselves together without it, and light bends around empty patches of space as if tugged by invisible hands. Yet after decades of hunting, we've never caught a single particle of it. The search has turned into a cosmic detective story with two prime suspects. First, WIMP, weakly interacting massive particles, theoretical heavyweights that barely touch normal matter, slipping through our detectors like ghosts. Then there's the underdog, actions, hypothetical ultralight particles that could flow through the cosmos like an intangible breeze. Laboratories' deep underground hunt for WIMP in vats of liquid xenon, while experiments like ADMX listen for actions converting into radio waves in powerful magnetic fields. So far, silence, but the plot thickens. Some galaxies, like NGC 1052, seem to have almost no dark matter at all, defying expectations. Others show gravitational effects without the expected dark matter halos, as if the universe forgot to follow its own rules. Could dark matter not be particles, but primordial black holes from the dawn of time? Or is our understanding of gravity itself fundamentally flawed? Modified Newtonian dynamics suggests tweaking gravity's equations could erase the need for dark matter entirely, but it struggles to explain all the cosmic evidence. Here's what keeps scientists awake at night. Dark matter isn't just a missing puzzle piece, it's the frame holding the puzzle together. Without it, galaxies would fly apart, cosmic webs wouldn't form, and the universe as we know it couldn't exist. Yet it refuses to show its face, leaving us with a haunting truth. We're surrounded by an ocean of the unknown, every galaxy and star merely floating on its surface, while the depths below remain utterly dark. If dark matter is the universe's hidden scaffolding, then dark energy is the mysterious hand that's tearing it all apart. Picture this: You throw a ball into the air, expecting it to slow down and fall back to Earth. But instead, it shoots upward faster and faster, vanishing into the sky. That's the baffling reality of our cosmos, an expansion that should be slowing due to gravity, but is actually accelerating, defying every expectation. The story of dark energy begins with a cosmic candle, Type Ia supernova. These exploding stars burn with such predictable brightness that astronomers use them as standard candles to measure vast distances. In the late 1990s, two separate research teams were studying these supernovae to calculate how fast the universe's expansion was slowing down. The shock came when their data revealed the opposite. The universe wasn't just growing, it was speeding up, as if some invisible force were pushing everything apart. The realization was so profound it earned them the Nobel Prize in 2011. Here's where things get truly strange. Dark energy isn't just another unknown. It makes up nearly 70% of the universe's total energy content, dwarfing both dark and ordinary matter. Yet we have no idea what it actually is. The leading candidate, Einstein's cosmological constant, a sort of background energy woven into the fabric of space itself. He originally proposed it as a fudge factor to keep the universe static, later calling it his greatest blunder when expansion was discovered. Now, ironically, it's the frontrunner to explain acceleration. But there's a problem. Quantum physics predicts this energy should be 10 to the power of 120 times stronger than what we observe. That's a discrepancy so vast it's been called the worst theoretical prediction in history. Alternative theories abound. Some suggest dark energy isn't constant at all, but a dynamic field they've dubbed quintessence, which could change over time. Others propose that gravity itself behaves differently on cosmic scales, requiring a rewrite of Einstein's equations. Then there's the radical idea that we're seeing the fingerprints of parallel universes in a vast multiverse, their gravity subtly tugging on ours. The implications are staggering. If dark energy continues unchecked, it could lead to a big rip where even atoms are torn apart in the distant future. Or it might fade away, allowing gravity to crunch everything back into a singularity. Right now, instruments like the Dark Energy Survey and the upcoming Euclid Space Telescope are mapping billions of galaxies to trace expansion's history, hunting for clues in the subtle warping of light and the distribution of cosmic structures. What makes dark energy so unnerving isn't just its dominance, it's the way it exposes how little we grasp about the universe's true nature. We're left staring at equations that describe an effect without revealing its cause, like watching shadows dance while the puppeteer remains unseen. In a cosmos where even nothingness pushes harder than gravity, the only certainty is this: the greatest forces shaping reality might be the ones we understand least. Somewhere beyond the Milky Way's glittering sprawl, an invisible behemoth is yanking entire galaxies toward it at breakneck speeds, and we can't even see it. Welcome to the Great Attractor, a gravitational anomaly so powerful it bends the motion of hundreds of thousands of galaxies, including our own. Picture a cosmic whirlpool, its current dragging everything nearby into an unfathomable abyss. The weirdest part, it's lurking behind what astronomers call the Zone of Avoidance, a dusty blind spot created by our galaxy's own bulk, blocking nearly a fifth of the visible universe from view. The first hints emerged in the 1970s when scientists noticed something odd. Galaxies in our cosmic neighborhood weren't moving randomly. Instead, they streamed toward a single point in the constellation Centaurus at over 2 million kilometers per hour. The culprit, a concentration of mass so immense it warps space-time itself with the gravitational pull of quadrillions of suns. But when researchers pointed telescopes in that direction, they found nothing obvious, just our own galaxy's star-choked disk obscuring the view, like trying to spot a lighthouse through a blizzard. So what is this hidden titan? One theory points to the Shapley supercluster, a staggering assembly of galaxies about 650 million light-years away. the most massive structure in our local universe. Imagine a sprawling city of galaxies, their combined gravity creating a funnel that even the Milky Way can't resist. Yet calculations suggest Shapley alone might not account for all the pull. Could there be something even bigger, something darker, lurking in the void? Some propose vast sheets of dark matter, cosmic filaments weaving an invisible web that tugs on everything in its reach. The mystery deepens when you consider our fate. The Milky Way, along with the entire local group of galaxies, is racing toward the Great Attractor at a blistering speed. But here's the twist: we'll never reach it. Dark energy's relentless push is accelerating the universe's expansion so fast that the attractor's grip will eventually loosen, leaving us forever in its wake. It's as if the cosmos is playing a cruel game of keep away, dangling secrets just beyond our grasp. Efforts to pierce the zone of avoidance continue, with infrared and radio telescopes peeling back the Milky Way's dusty veil. Each new glimpse reveals more galaxies, more clusters, yet the Great Attractor's core remains elusive. Whether it's Shapley's influence, an even grander structure, or something we haven't dreamed of yet, one thing is clear: the universe hides its greatest wonders in plain sight, if only we know how to look. Of all the stars in our cosmic backyard, none has caused as much confusion and wild speculation as KIC 8462852, better known as Tabby's star. Named after astronomer Tabitha Boyajian, who led the team that first spotted its bizarre behavior, this star doesn't twinkle, it flickers like a light bulb with a loose connection. But here's the twist: its dimming isn't predictable or gentle. At times, its light drops by a staggering 22%, as if something massive and irregular is passing in front of it. And that's just the beginning of the mystery. The strangeness came to light in 2015, when citizen scientists combing through data from NASA Kepler telescope flagged the star as weird. Most exoplanets cause tiny, periodic dips in starlight, perhaps 1% every few days. Tabby's star defied all norms. Its dips were erratic, deep, and lasted for days or weeks with no discernible pattern. One particularly dramatic event, dubbed Elsie, saw the star's brightness plummet by 15% over nearly a week before slowly recovering. Another series of dips, called the anchor events, occurred years later, proving this wasn't a one-time glitch. Theories erupted faster than solar flares. The most tantalizing and controversial suggested a Dyson swarm, a hypothetical megastructure built by an advanced civilization to harvest a star's energy. Imagine a vast network of orbiting solar panels blocking light in irregular clumps. It was a sci-fi dream come to life, but skepticism soon followed. After all, extraordinary claims require extraordinary evidence. Enter the dust hypothesis. Further observations revealed that the star dimmed more in blue light than in red, a telltale sign of fine particles scattering shorter wavelengths, just like Earth's atmosphere reddens the setting sun. The culprit, likely clouds of comet fragments or planetary debris, stirred up by gravitational chaos or a recent collision. Some researchers even proposed a disintegrating moon or a rogue planet with a massive ring system. Yet the puzzle isn't fully solved. Dust can't easily explain historical data showing the star's overall brightness fading by 14% over a century, a trend verified by old photographic plates. And why does the dust seem to cluster in such bizarre, uneven ways? Instruments like the James Webb Space Telescope are now scrutinizing the star's infrared signature, hunting for heat that dust should emit. What makes Tabby's star so compelling isn't just the unanswered questions, it's the way it forces us to rethink how stars should behave. Whether it's aliens, cosmic dust, or something entirely new, this flickering enigma reminds us that the universe is full of surprises hiding in plain sight. The universe is unimaginably vast, with trillions of stars, many hosting planets in the so-called Goldilocks zone where life could thrive. Given those odds, the cosmos should be teeming with civilizations. So where is everybody? That's the Fermi paradox in a nutshell, the glaring contradiction between the high probability of extraterrestrial life and the eerie silence we've encountered so far. Named after physicist Enrico Fermi, who famously blurted out, "But where are they?" during a lunchtime discussion in 1950, this paradox has spawned theories ranging from the sobering to the downright chilling. One of the most unsettling explanations is the Great Filter, a hypothetical barrier that prevents life from advancing to interstellar communication or colonization. Think of it as a cosmic sieve catching civilizations before they can spread. The terrifying question is whether the filter lies in our past or our future. If it's behind us, like the improbable jump from simple cells to complex life, that's reassuring. It means we've beaten the odds. But if it's ahead, nuclear war, climate collapse, rogue AI, it implies catastrophe lurks in our destiny. The filter could even be something we haven't considered yet, like a galactic-scale extinction event that wipes out advanced civilizations periodically. Then there's the zoo hypothesis, a gentler but no less bizarre take. Imagine Earth as a nature preserve, deliberately left untouched by advanced aliens who observe us like animals in a cosmic safari park. It's a twist on Star Trek's Prime Directive, except in this scenario we're the ones being kept in the dark. While it explains the silence, it raises another question. Why would every civilization agree to such secrecy? Other theories are even more creative. Maybe interstellar travel is simply too impractical, with physics locking civilizations inside their own solar systems. Or perhaps we're searching for the wrong things. Alien probes might already be here, disguised as asteroids or operating at scales too small or too vast for us to notice. There's even the haunting dark forest hypothesis, which paints the universe as a lethal game of hide and seek, where civilizations stay silent to avoid attracting predators. Yet the paradox persists. Every wow signal or eerie exoplanet discovery rekindles hope, but the silence remains. New telescopes like the James Webb or projects like SETI laser scans keep pushing the search forward, scanning for technosignatures, traces of alien technology in distant atmospheres or energy emissions. The answer, when it comes, might not be a radio message or a flying saucer, but something far stranger. Until then, the Fermi paradox stands as both a challenge and a warning. In a universe that should be loud with life, our solitude is either a fluke or a sign of something we've yet to understand. In October 2017, astronomers spotted something streaking through our solar system that shouldn't have been there, a visitor from another star. Named Oumuamua, Hawaiian for scout, this interstellar object was unlike anything we'd ever seen. It wasn't just its origin that puzzled scientists, it was the way it moved. Instead of gliding smoothly under gravity's pull, Oumuamua sped up as it raced away from the sun, as if pushed by an invisible hand. And its shape, forget the typical lumpy asteroid. This thing was flat, maybe 10 times as long as it was wide, tumbling through space like a cosmic pancake. Theories scrambled to explain its bizarre acceleration. At first, astronomers assumed it was a comet venting gas as it warmed near the sun. But telescopes found no telltale tail, no dusty halo, nothing to suggest the usual outgassing. Then came the wilder idea: could Oumuamua be a light sail, a fragment of alien technology propelled by starlight? Harvard astronomer Avi Loeb championed this hypothesis, pointing out that its thin, reflective surface and unexpected boost matched predictions for an artificial object. The scientific community bristled, calling it sensationalism, but Loeb countered, shouldn't we at least consider the possibility when nature fails to provide a tidy answer? The debate hinges on Oumuamua's strangeness. Solar system comets accelerate too, but they leave visible trails, and while some asteroids are elongated, none match Oumuamua's extreme proportions. Then there's its brightness, flickering erratically as it tumbled, suggesting a surface unlike the rough, cratered terrain of typical space rocks. Could it be a shard of a shattered planet, sheared off by a distant collision? Or a cosmic dust bunny, a lightweight aggregate of interstellar debris. The truth slipped away as Oumuamua vanished beyond Pluto, too faint to track further. But its legacy lingers. New telescopes like the Vera Rubin Observatory stand ready to catch the next interstellar visitor, armed with lessons from this enigmatic scout. Whether it was a weirdly shaped comet, a fragment of alien tech, or something else entirely, Oumuamua forced us to confront an uncomfortable truth. The universe is stranger than our textbooks, and sometimes the most profound mysteries arrive unannounced, then slip through our fingers before we can grasp them. For decades, whispers have circulated about an ancient object silently orbiting Earth, a relic from an advanced alien civilization watching us from the shadows of space. They call it the Black Knight satellite, and its legend is a tangled web of Cold War paranoia, misidentified space junk, and a stubborn myth that refuses to die. The story begins in 1954 when newspapers reported 2 mystery satellites orbiting Earth, impossible at the time, since humanity hadn't even launched Sputnik yet. Conspiracy theorists latched onto this as proof of extraterrestrial surveillance, claiming governments had known for years. But the real spark came in 1960 when Time magazine published a story about the U.S. Navy detecting a dark, tumbling object in polar orbit, an orbit so unusual for human-made satellites that speculation ran wild. Amateur radio operators added fuel to the fire, claiming to intercept strange signals they attributed to the Black Knight. Then came the clincher, a grainy 1998 NASA photo from the STS-88 mission, showing a bizarre, angular object against the curvature of Earth. To believers, this was undeniable proof. To skeptics, a lost thermal blanket from the International Space Station, drifting lazily in the void. So what's really lurking up there? Space debris experts point to the blanket explanation as the most plausible. Thermal insulation breaking loose during an ISS repair is a well-documented occurrence. The unusual orbit, a trick of orbital mechanics where objects in high-inclination orbits appear to move counter to Earth's rotation, and those eerie radio signals. More likely natural phenomena or earthly interference misinterpreted through the fog of excitement. Yet the myth endures, bolstered by cherry-picked NASA transcripts mentioning unidentified objects, common jargon for routine space debris, and viral internet posts stitching together half-truths. What makes the Black Knight so compelling isn't just the mystery, it's the human desire for hidden histories, for proof that we're not alone, or that advanced civilizations once walked among the stars. In a universe full of unexplained phenomena, sometimes the most fascinating mysteries aren't written in the cosmos, but in our own relentless imagination. Galaxies might seem like unchanging islands of stars, but peer into their history, and you'll find a cosmic buffet where the biggest devour the smallest. This is galactic cannibalism, a slow, violent dance where massive galaxies grow by tearing apart and absorbing their smaller neighbors. Our own Milky Way is no innocent bystander. It's a seasoned predator with scars to prove it. Take the Gaia sausage, for example. This strange collection of stars orbiting the Milky Way's core isn't just a random grouping, it's the mangled remains of a dwarf galaxy, our Milky Way, shredded and consumed 10 billion years ago. Astronomers call it a sausage because of the elongated, chaotic orbits these stars now follow, like crumbs scattered after a feast, but that's just the appetizer. The Milky Way's halo is littered with stellar streams, ribbons of stars stretched into graceful arcs by gravity's pull, each marking a past collision. One of the most famous, the Sagittarius dwarf spheroidal, has been orbiting our galaxy for billions of years, leaving behind trails of stars as it's slowly torn apart. Now fast forward 4 billion years, and the Milky Way faces its own fate on the menu. Andromeda, our nearest galactic neighbor, is hurtling toward us at over 250,000 miles per hour. When we collide, gravity will warp both galaxies into a chaotic swirl of stars, gas, and dust, a celestial ballet where entire solar systems are flung into new orbits. But here's the twist: galaxies don't crash like cars. They merge like two clouds of smoke, their stars so far apart that direct collisions are rare. Instead, gravity reshapes them, creating a new, larger galaxy dubbed Milkdromda, with a puffed-up core and swirling tidal tails of ejected stars. Simulations show this process could fling our solar system to the galaxy's outskirts, leaving future civilizations with a night sky devoid of the Milky Way's familiar band. What makes galactic cannibalism so fascinating isn't just the violence, it's how it shapes the universe's structure. Every massive galaxy we see today grew by consuming others, a cycle as old as time itself. Even now, the Milky Way is digesting the Large Magellanic Cloud, a satellite galaxy whose fate is sealed. In the grand cosmic kitchen, the rule is simple: eat or be eaten. Deep in the constellation of Boötes lies a cosmic desert so vast it defies logic, a spherical void stretching 330 million light-years across, containing only a handful of galaxies where there should be thousands. Picture holding up a basketball to the night sky. That empty space would cover a patch of universe that, by all odds, should sparkle with countless stars. Instead, the Boötes void is a staggering absence, a near-perfect sphere of nothingness that makes astronomers question everything they know about how the universe structures itself. The void was first spotted in 1981 when astronomer Robert Kirshner and his team noticed an unusual gap in galaxy surveys. At first, they thought it might be an error, a dusty patch obscuring the view. But deeper observations confirmed the terrifying truth: this was no illusion. The void was real, and it was far emptier than any theoretical model predicted. Most large-scale cosmic voids span 100 million light-years at most, with at least some galaxies sprinkled throughout. The Boötes void isn't just bigger, it's emptier, with only 60 galaxies detected where there should be 10,000. The odds of such a void forming naturally, less than 1 in a million. So how does a hole this vast exist? One theory points to a phenomenon called cosmic inflation, where tiny quantum fluctuations in the early universe ballooned into massive empty regions as space expanded faster than light. Another wild idea suggests the void might be the imprint of an ancient collision between our universe and a parallel one, a cosmic bruise left behind in the fabric of reality. Or perhaps it's evidence of something even stranger: exotic physics like dark energy acting in ways we haven't yet imagined, sculpting the cosmos into shapes that shouldn't be possible. Then there's the mini-void paradox. Within the Boötes void, even the few galaxies that do exist aren't arranged randomly. They cluster along filaments, as if huddling together for warmth in an unimaginably cold expanse. This pattern defies the standard model of galaxy formation, which assumes matter spreads relatively evenly. Some researchers argue these filaments might be the last remnants of a region that was once normal, slowly drained of galaxies by an unseen gravitational force. Others speculate the void could be a bubble universe in its infancy, a pocket of space cut off from the rest of reality by some long-forgotten cosmic quirk. The Boötes void isn't just a curiosity, it's a challenge. If voids this large can form naturally, our understanding of dark matter and cosmic structure is incomplete. If they can't, then we're missing something fundamental about the universe's architecture. Every telescope pointed at this emptiness is searching for clues in the darkness, probing the void not just for what's missing, but for what its silence might be trying to tell us. In the vast emptiness between planets, where gravity's grip weakens and the sun's warmth fades to a whisper, two spacecraft defied every expectation, not by what they found, but by how they moved. NASA Pioneer 10 and 11, launched in the early 1970s to explore the outer solar system, became famous for an entirely unintended reason. They slowed down when no one thought they should. For decades, this tiny deceleration, just a fraction of what Newton's laws predicted, baffled scientists, fueling whispers of new physics or even unseen dark matter tugging at the probes. They called it the Pioneer Anomaly, and it became one of space's most stubborn mysteries. The discrepancy was subtle but persistent. As the pioneers raced toward the edges of the solar system, ground stations tracking their radio signals noticed something odd. Each probe was falling behind its expected trajectory by about 300 miles per year, a deviation no amount of gravitational math could explain. At first, scientists suspected mundane causes, a fuel leak, a software glitch, or maybe the drag of microscopic dust. But as years turned to decades, and both probes, now billions of miles apart, showed the same anomaly, the possibilities grew stranger. Could Einstein's theory of gravity need tweaking at cosmic scales? Was some unknown force, dark energy, quantum foam, even higher dimensions, tugging at the spacecraft? Then came the breakthrough and the irony. After 30 years of head-scratching, a team of researchers realized the answer wasn't hiding in the shadows of new physics, but in the glow of old-fashioned heat. The pioneers, powered by plutonium-fueled radioisotope generators, emitted warmth as they operated. That heat radiated unevenly from their boxy bodies, creating a tiny but constant push backward like a car idling with its parking brake slightly engaged. When scientists meticulously modeled every surface and watt of thermal emission, the anomaly vanished. The culprit, the probe's own design, reflecting heat in a way no one had fully accounted for. Yet the Pioneer Anomaly's legacy endures. It's a reminder that even the most precise instruments carry hidden biases, and that the universe often hides its secrets in plain sight. For years, the anomaly sparked debates about modified gravity theories, some of which still linger at the fringes of cosmology. And while the solution turned out to be thermal, the mystery itself was anything but mundane, a testament to how easily the familiar can masquerade as the extraordinary when viewed from the right angle. The next time a spacecraft behaves oddly, scientists will remember the pioneers. Sometimes the universe's greatest puzzles aren't written in the stars, but in the unintended consequences of our own creations. Imagine a light so brilliant it outshines an entire galaxy, not from billions of stars, but from a single point no larger than our solar system. This is the power of a quasar, the universe's most energetic phenomena, beaming across space like a cosmic lighthouse from the dawn of time. First discovered in the 1950s as mysterious radio sources, these objects initially baffled astronomers. Their spectra looked nothing like stars or galaxies, and their distances, once measured, revealed something even more shocking. Quasars exist billions of light years away, meaning we're seeing them as they were when the universe was less than a tenth of its current age. At the heart of every quasar lies a supermassive black hole, but not the quiet, dormant giants like Sagittarius, a star at our Milky Way's center. These are black holes in their most ravenous phase, devouring gas and dust so voraciously that the infalling matter heats up to millions of degrees, glowing brighter than anything else in the cosmos. The energy released is staggering. Some quasars emit thousands of times more light than our entire galaxy, all from a region smaller than Pluto's orbit. Surrounding the black hole, a spinning disk of superheated material acts like an inefficient engine, converting matter into radiation with terrifying efficiency. But here's the puzzle: how did these monsters grow so big, so fast? The quasar SDSS J1342+0928, for example, houses a black hole with 890 million solar masses, and it's visible from just 690 million years after the Big Bang. That's like finding a fully grown blue whale in a swimming pool. There simply wasn't enough time in the early universe for such behemoths to form under current theories. Did they start as seed black holes from collapsed supermassive stars, or could they have formed directly from dense primordial gas clouds? The answer might rewrite our understanding of cosmic evolution. Quasars aren't just bright, they're messy eaters. As material spirals inward, magnetic fields funnel some of it into blazing jets that shoot out at nearly light speed, stretching millions of light years into space. These jets can carve bubbles in intergalactic gas, influence star formation in entire galaxy clusters, and even act as particle accelerators, flinging cosmic rays across the universe. The Quasar 3C273, studied by the Hubble Space Telescope, revealed something even wilder. Its jet, packed with enough energy to power 10 trillion suns, showed helical twists like a spinning fire hose unleashed into the void. What makes quasars truly humbling isn't just their power, it's their role as time capsules. Their light, traveling for billions of years before reaching us, carries fingerprints of the early universe's conditions. By studying the absorption lines in quasar spectra, astronomers have mapped the cosmic web, the vast network of gas filaments connecting galaxies. They've even detected shadows cast by the first clouds of hydrogen, revealing how the universe transitioned from opaque to transparent. Yet for all we've learned, quasars still guard their secrets fiercely. Why did their golden age, peaking around 10 billion years ago, fade? Most quasars today are dormant, their black holes starved of fuel. Did the universe simply run out of gas, or did something more fundamental change? And what about blazars, quasars whose jets point directly at Earth, flooding our telescopes with gamma rays? These extreme versions hint that even now, we're only scratching the surface of their mysteries. In the end, quasars aren't just relics. They're reminders that the universe's infancy was a place of unimaginable violence and beauty, where the rules we take for granted were still being written. In the afterglow of the Big Bang, a faint whisper lingers, the cosmic microwave background, or CMB, a snapshot of the infant universe just 380,000 years old. This ancient light should be random, a uniform sea of tiny temperature fluctuations left over from the universe's fiery birth. But when scientists mapped it with unprecedented precision, they found something unsettling. The fluctuations aren't random. Instead, they align along a mysterious axis, as if the universe itself has a preferred direction. Astronomers call it the axis of evil, a name that hints at just how deeply this anomaly challenges our understanding of reality. The discovery came in 2005 when data from NASA WMAP satellite revealed an eerie pattern. The CMB's hot and cold spots weren't scattered like dice rolls. They lined up along a plane that slices through the constellations of Leo and Aquarius. Worse yet, this axis also aligns with the ecliptic plane, the path Earth follows around the Sun. The odds of such an alignment happening by chance, less than 1 in 1,000. To cosmologists, this was like discovering that every galaxy in the sky was subtly pointing at your backyard. The implications are dizzying. The CMB is supposed to be the ultimate cosmic fingerprint, a relic of a time before stars or galaxies existed. If its patterns aren't random, it could mean our universe isn't isotropic, that the laws of physics change depending on which way you look. That would upend the Copernican principle, the foundational idea that Earth holds no special place in the cosmos. Suddenly, we're left wondering, are we seeing evidence of a universe shaped by forces beyond our current models, or is there a hidden flaw in how we interpret the data? Skeptics argue the axis might be an illusion, a trick of statistics, or an artifact of foreground interference, like dust in our own galaxy muddying the signal. Others point to more exotic possibilities. Could it be a relic of collisions with other universes in a vast multiverse, leaving a bruise on our cosmic horizon? Or might it trace back to before the Big Bang, a shadow of some primordial structure that set the universe spinning in a preferred direction, the most radical suggestion? That we're seeing the imprint of an unseen, universe-spanning force, a cosmic magnetic field, or a defect in spacetime itself, left over from the universe's quantum origins. Yet the mystery deepens. Later observations by the Planck satellite confirmed the anomaly, though with weaker significance. Some researchers now argue the alignment might not be in the CMB itself, but in our motion through space. The local group of galaxies, including the Milky Way, is racing toward the constellation Centaurus at over 600 kilometers per second, a relic of gravitational pulls from distant superclusters. Could this motion stretch and skew the CMB's patterns, creating the illusion of an axis? If so, it would mean the axis of evil isn't a flaw in the universe but in our perspective, like trying to read a billboard through a rain-streaked windshield. What makes the axis so unnerving isn't just the potential for new physics, it's the way it exposes how fragile our cosmic assumptions might be. For decades, we've modeled the universe as smooth and uniform, its quirks averaged out over vast scales. But if the CMB harbors a preferred direction, it could mean the universe isn't just lumpy with galaxies. It might be textured in ways we're only beginning to grasp. Until we crack this enigma, the axis of evil stands as a ghost in the machine of cosmology, a whisper that the universe, for all its apparent chaos, might still be hiding a secret order. Most stars die by the rules collapsing into black holes, fading as white dwarfs, or exploding in spectacular supernova, but some refuse to follow the script. Enter zombie stars, cosmic anomalies that cheat death, reigniting after their supposed demise in ways that defy every textbook on stellar evolution. The most puzzling of these are the survivors of Type Ia supernova, explosions so uniform they're used as cosmic mile markers. These stellar phoenixes shouldn't exist, yet here they are, flickering back to life like ghosts in the machine of the universe. Take the case of supernova 2012Z, spotted in the galaxy NGC 1309. When this star exploded, astronomers expected it to vanish forever, leaving behind only a faint remnant. Instead, it lingered, glowing stubbornly for years with a warmth that shouldn't have been possible. The culprit, a half-finished explosion. Unlike typical Type Ia supernova, which obliterate their white dwarf progenitors completely, this one detonated unevenly, leaving a charred stellar core behind. Like a firework that fizzles but doesn't burst, the star's outer layers blasted away while its heart kept beating, now fueled by unstable nuclear reactions that defied all models. Then there's LP 40 to 515, dubbed the Freddy Krueger star for its habit of resurrecting. Originally a white dwarf, a dense, Earth-sized ember left after a sun-like star exhausts its fuel, it should have faded into darkness. But instead, it's been caught flaring up repeatedly over decades, brightening by a factor of 15 in mere hours. The leading theory, a cannibalistic relationship with a companion star, siphoning just enough gas to trigger mini-explosions without fully reigniting. Imagine a campfire that keeps sparking back to life with a single drop of gasoline over and over. Yet the real head-scratchers are the supernova imposters, stars like IPTF-14 HLS. In 2014, it flared up like a standard supernova, then did it again 5 times in 2 years, as if stuck in a cosmic replay. Spectra revealed layers of debris moving at wildly different speeds, suggesting multiple explosions rippling through the same star. One radical explanation posits a pulsating pair instability supernova, where a massive star's core becomes so hot it converts energy into matter and antimatter, triggering cycles of collapse and rebirth. It's like watching a stellar Russian nesting doll, each layer hiding another explosion waiting to happen. What makes zombie stars so unsettling isn't just their defiance of physics, it's what they reveal about our blind spots. For decades, Type Ia supernova were considered the universe's most reliable standard candles, their consistent brightness helping measure cosmic distances and even prove dark energy exists. But if some white dwarfs survive these blasts or explode incompletely, those measurements might need recalibrating. Could slight variations in these standard explosions explain lingering discrepancies in the Hubble constant, the universe's expansion rate? The deeper we look, the more these stellar undead multiply. Some pulsar spinning neutron stars exhibit glitches, sudden speed-ups in rotation that mimic a reawakening. Others, like the Magnetar SGR 0418 plus 5729, erupt with gamma-ray flares years after their supposed deaths, as if something inside is still violently alive. Even our sun might join the ranks posthumously. Models suggest white dwarfs can reignite if they accrete enough helium, potentially becoming born-again giants billions of years after fading. In the end, zombie stars aren't just cosmic oddities, they're reminders that the universe loves exceptions. For every rule we write about how stars live and die, there's a rebel out there rewriting the script, forcing us to question what we thought we knew. And as telescopes grow sharper, we're left wondering, how many more of these stellar ghosts are lurking in the darkness, waiting to rise? Imagine a world without sunrise, no golden dawn, no blistering noon, just perpetual night stretching endlessly in every direction. This is the existence of rogue planets, cosmic nomads untethered to any star, drifting through the void like ghosts. Astronomers once thought these wanderers were rare, but recent surveys suggest they might outnumber stars in our galaxy, a hidden population of billions silently threading the darkness between sunlit systems. How do planets end up alone? Some are born that way, condensing from gas clouds too small to ignite into stars, like failed solar systems with only one member. Others get violently evicted. Picture a young star system, chaotic with gravitational tugs as planets jockey for position. A close encounter with a sibling world or the pull of a passing star can hurl a planet clear of its home, sending it careening into interstellar space at speeds topping 100,000 miles per hour. Simulations show our own Jupiter might have nearly suffered this fate, saved only by Saturn's stabilizing influence billions of years ago. But here's where it gets fascinating. Rogue planets might not be the frozen wastelands we assume. Tidal forces from their formation or the decay of radioactive elements could keep their cores warm for eons, encase that heat under a thick ice shell, and you've got a recipe for sprawling subsurface oceans, liquid water in perpetual darkness, shielded from space's chill. Europa and Enceladus, the famed ocean moons in our solar system, prove such environments can exist, now scaled at up to Earth-sized rogue worlds, and suddenly the idea of life without starlight doesn't seem so far-fetched. The best evidence comes from microlensing, a cosmic quirk where a rogue planet's gravity briefly bends light from a distant star, revealing its presence like a lens flaring in the dark. Projects like Japan's MOA and Korea's KMT-net have catalogued hundreds this way, some as close as a few dozen light-years. One, labeled Ogle 2016 BLG 1928, weighs just a few times more than Earth, suggesting small, rocky rogues might be common. Others, like the free-floating gas giant CFBD SIR 2149-0403, still glow faintly from their formation heat, detectable in infrared despite having no sun to warm them. The hunt for these wanderers is accelerating. NASA's upcoming Nancy Grace Roman Space Telescope aims to spot thousands via microlensing, while radio telescopes like Oumuamua scour young star clusters for ejected infant planets. There's even speculation that our solar system might harbor a captured rogue planet 9. The hypothesized giant lurking beyond Neptune could be an immigrant snatched by the sun's gravity long ago. What truly captivates isn't just their abundance, but their potential as cosmic arcs. If life can emerge in the sunless depths of a rogue planet's ocean, sustained by hydrothermal vents or chemical reactions, these worlds could be ferrying biology between stars, seeding the galaxy not with comets but with entire habitable environments. It's a staggering thought. Beneath the ice of some drifting wanderer, entire ecosystems might thrive in eternal night, oblivious to the stars they'll never see. In a universe teeming with light, the darkest corners might hide the most unexpected sparks of life. At the frozen edge of our solar system, where sunlight dwindles to a faint glimmer, lies a boundary so abrupt it's as if someone drew a line in the cosmic sand. Astronomers call it the Kuiper Cliff, a mysterious drop-off in the number of icy objects beyond 50 astronomical units from the Sun, as if the Kuiper belt simply ends. This isn't just a gradual thinning like the fade out of a song. It's a sudden, dramatic cutoff that defies everything we know about how planetary systems form. The Kuiper Belt, home to Pluto and thousands of other icy bodies, was expected to extend smoothly for hundreds of its population dwindling slowly with distance. Instead, surveys like the Outer Solar System Origins project reveal a stark emptiness beyond the cliff, with far fewer objects detected past this invisible barrier than models predict. It's as if a cosmic broom swept the outer reaches clean, leaving scientists scrambling for explanations. One tantalizing possibility: the gravitational hand of Planet 9, the hypothetical giant lurking in the distant dark. If a massive, undiscovered world orbits hundreds of from the Sun, its gravity could have shepherded Kuiper Belt objects into clustered orbits, clearing out the region beyond. Think of it like a celestial bulldozer carving a path through the icy debris. The math shows Planet 9's influence could explain the cliff's sharp edge, as well as the peculiar orbits of some extreme trans-Neptunian objects like Sedna. But not everyone's convinced. Critics argue observational biases could be skewing the data. Detecting small, dim objects at such distances is like trying to spot a charcoal briquette in a pitch-black room. New Horizons' flyby of Arakoth, a Kuiper Belt object just 44 out, revealed how much we've underestimated the belt's complexity. Could better telescopes unveil a hidden population of objects beyond the cliff, rendering the mystery a mere artifact of incomplete data? Then there's the wild card, a primordial black hole. Some theorists propose a grapefruit-sized black hole, left over from the Big Bang, could be lurking in the outer solar system, its gravity mimicking Planet 9's effects. While far-fetched, it's a reminder that the universe often reserves its strangest explanations for the most puzzling gaps in our knowledge. What makes the Kuiper Cliff so compelling isn't just the unanswered questions. It's the reminder that even in our own cosmic backyard, the rules can change without warning. Whether it's an unseen planet, an observational blind spot, or something even stranger, this frozen frontier proves one thing: the solar system's story is still being written, and its final chapters might hold the biggest surprises. Picture a world where diamonds aren't rare gems, they're the ground beneath your feet. Meet 55 Cancri, a planet so extravagantly rich in carbon that scientists speculated could be coated in layers of diamond, glinting like a cosmic crown jewel. But don't let the sparkle fool you. This is no paradise. This super-Earth, twice the size of our own planet and 8 times as massive, orbits so close to its sun that a single year lasts just 18 hours, and its surface is a broiling nightmare of molten lava and crushing pressures. Discovered in 2004, 55 Cancri circles a star 40 light-years away in the constellation Cancer. At first glance, it seemed like just another rocky exoplanet, but closer study revealed something extraordinary. Its composition is likely dominated by carbon, the same element that forms diamonds. Under the intense heat and pressure of its interior, that carbon could crystallize into vast diamond deposits, possibly making up a third of the planet's mass. Imagine mountain ranges of gemstone, gleaming under the glow of a perpetual orange sunrise. Yet this world's beauty is skin-deep. Its surface temperatures soar to 2,700 degrees Celsius, hot enough to vaporize rock and create seas of liquid lava. The planet's dayside, forever locked facing its star, is a hellscape of glowing magma, while its nightside might host rivers of molten silicon. Even its atmosphere, if it has one, is likely a toxic soup of hydrogen and helium stripped away by blistering stellar winds. What makes 55 Cancri truly fascinating isn't just its extremes, it's the puzzle of how such a carbon-rich world formed. Most rocky planets like Earth are built from silicates and oxygen. But in systems where carbon outpaces oxygen during planetary birth, you get worlds where carbon compounds dominate. Think graphite crusts, diamond-riddled mantles, and even hydrocarbons raining from the sky. Some models suggest the planet might have started as a gas giant's core, its outer layers ripped away by the star's gravity, leaving behind a dense, carbon-packed remnant. The diamond planet also challenges our assumptions about habitability. While superficially similar in size to Earth, its environment couldn't be more alien. Yet it raises a tantalizing question. If carbon-rich planets can exist, could they harbor exotic forms of chemistry or even life? On Earth, carbon is the backbone of biology. On 55 Cancri E, under those crushing pressures and scorching temperatures, who knows what strange molecular architectures might arise? Observations with the James Webb Space Telescope aim to probe the planet's atmosphere, hunting for traces of carbon monoxide or other compounds that could confirm its glittering nature. Until then, 55 Cancri E remains a dazzling enigma, a world where the universe's most coveted gem is as common as dirt, and where the line between treasure and torment is as thin as a razor's edge. The universe is expanding. We've known that for nearly a century, but how fast it's expanding has become one of the most hotly debated questions in modern cosmology. Enter the Hubble tension, a stubborn discrepancy in the measured expansion rate of the cosmos, one that refuses to fade even as our tools grow sharper. On one side, we have the cosmic microwave background, the afterglow of the Big Bang, suggesting an expansion rate of about 67 kilometers per second per megaparsec. On the other, observations of nearby stars and supernova peg the number closer to 73. That gap might sound small, but in the precise world of cosmology, it's a yawning chasm, one that could force us to rewrite the very laws governing the universe. So why does this mismatch matter? The cosmic microwave background, or CMB, acts like a frozen snapshot of the infant universe, its patterns encoding the seeds of everything that followed. When scientists plug those early conditions into the standard cosmological model, our best blueprint for how the cosmos evolved, they predict today's expansion rate with elegant precision. Yet when astronomers measure the actual movement of galaxies and exploding stars in our cosmic neighborhood, the numbers refuse to align. It's as if you baked a cake following a trusted recipe, only to pull out something entirely different from the oven. Either we're misreading the ingredients, or there's a hidden step no one told us about. The most tantalizing possibility, new physics. Some theorists argue dark energy, the mysterious force accelerating the universe's expansion, might be evolving, growing stronger or denser over time. Others suggest exotic flavors of dark matter or even extra dimensions subtly tweaking gravity's rules. Then there's the radical idea that our universe isn't perfectly uniform, that we're sitting in a local bubble of lower density, skewing nearby measurements like a funhouse mirror. If true, it would mean the cosmos isn't as smoothly mixed as we've assumed, with hidden wrinkles stretching across space-time. But skeptics aren't ready to abandon the textbooks just yet. Could the mismatch stem from something mundane, like unnoticed dust dimming distant supernova, or maybe the tools we're using, like the cosmic distance ladder built from Cepheid variable stars, have hidden biases? The stakes couldn't be higher. If the tension persists, it might hint at gaps in our understanding as profound as those that once forced Einstein to rethink gravity itself. New missions like the James Webb Space Telescope and the upcoming Nancy Grace Roman Telescope are doubling down on the hunt, cross-checking distances with unprecedented precision. Whatever they find, the Hubble tension isn't just a numbers game. It's a cosmic tug of war between the universe as we see it and the universe as we think it should be. And in that gap, lurking between expectation and observation, might lie the next great revolution in our understanding of reality. Most dying stars bow out in a blaze of spherical glory, their outer layers puffing away in perfect, symmetrical halos. Then there's the Red Rectangle Nebula, a cosmic rebel that defies every expectation with its sharp edges, geometric precision, and eerie glow. Located about 2,300 light-years away in the constellation Monoceros, this nebula looks less like a celestial smoke ring and more like a neon-lit X drawn across the void. Its bizarre structure has baffled astronomers since its discovery in the 1970s, offering a front-row seat to stellar death's strangest encore. At the heart of the red rectangle lies HD 44179, a binary star system where one sun-like star has begun shedding its outer layers in its death throes. Normally, this process creates the classic planetary nebula, a glowing orb of gas expanding evenly in all directions. But here, something's gone sideways, literally. Instead of a sphere, the expelled material forms two cone-shaped outflows crisscrossing at right angles, creating that distinctive rectangular silhouette when viewed edge-on. Imagine squeezing a spray bottle's nozzle in two perpendicular directions at once, painting the cosmos with glowing gas in precise, angular strokes. The nebula's color is just as puzzling as its shape. Most planetary nebulae shimmer in blues and greens from ionized oxygen and nitrogen. The red rectangle, true to its name, bathes space in a deep, blood-like crimson. This comes from a rare class of molecules called polycyclic aromatic hydrocarbons, or par-complex carbon chains that fluoresce when hit by starlight. Normally, these molecules break apart in the harsh environment around dying stars, but HD 44179's unique conditions, likely shielded by dense dust lanes, have turned it into a cosmic chemistry lab, cooking up these organic compounds in vast quantities. Some scientists even speculate the red rectangle could be seeding the galaxy with the building blocks of life, flinging carbon-rich material into space like a molecular sprinkler. Then there's the central star's dance partner. The binary companion isn't just a passive observer, it's actively sculpting the outflow. As the dying star sheds material, its companion's gravity funnels the gas into two opposing jets, pinching them into cones and whipping them into that X-shaped pattern. Dust grains swirling in this chaotic ballet might even explain the ladder-like rungs visible within the nebula's arms, giving it the appearance of a glowing spiderweb. But the red rectangle's true legacy might be what it teaches us about stellar afterlife. Most stars end up as white dwarfs surrounded by fading nebulae, but few leave behind such a precise architectural blueprint. Could this be a preview of our own sun's fate billions of years from now? Or is it a fluke of physics, a rare alignment of stellar winds and gravitational tugs that few systems replicate? Telescopes like Hubble and JWST continue probing its chemistry and structure, searching for clues in its crimson glow. What makes this nebula unforgettable isn't just its defiance of cosmic norms, it's the reminder that even in death, stars can create beauty beyond imagination. Against the dark canvas of space, the red rectangle stands as both a masterpiece and a mystery, a geometric whisper from a dying star that refuses to fade quietly. Black holes were supposed to be the universe's ultimate shredders, cosmic traps where anything that crossed the event horizon vanished forever, leaving no trace of its existence. But in the 1970s, Stephen Hawking dropped a bombshell. Black holes aren't so black after all. They leak. Through a bizarre quantum quirk, they emit faint radiation, slowly evaporating over eons until they pop out of existence. This revelation, now called Hawking radiation, solved one mystery while creating an even bigger one. If black holes evaporate, what happens to all the information they swallowed? According to quantum mechanics, information can never be truly destroyed. It might get scrambled, but it must persist. Yet Hawking's math suggested black holes obliterate it completely. This clash between gravity and quantum theory became the black hole information paradox, a puzzle so deep it's divided physicists for decades. At the heart of the paradox is a cosmic game of keep away. Imagine tossing a book into a black hole. The pages might be incinerated by tidal forces or stretched into spaghetti by gravity, but quantum rules insist the information, the story those pages told, must still exist somehow. Hawking originally argued that when the black hole radiates away, the information vanishes with it, violating quantum mechanics' sacred principle of unitarity. It's like burning a diary and claiming no copy of its words exists anywhere in the universe. To many physicists, that's tantamount to heresy. Enter the soft hair theory, a tantalizing breakthrough that might just reconcile these warring ideas. Proposed by Hawking and colleagues in 2016, it suggests black holes aren't entirely bald. Instead, they're fringed with ultra-low-energy quantum fields, soft hair, imprinted on their event horizons. Every particle that falls in could leave a subtle fingerprint in these fields, preserving information in a way we've yet to fully decipher. Think of it like a cosmic etch-a-sketch. The black hole's surface records faint traces of what falls in, even as the objects themselves are crushed beyond recognition. But the debate is far from settled. Some theorists champion the holographic principle, which posits that all the information in a black hole is smeared across its 2D surface like a hologram, with the 3D interior being an illusion. Others argue for firewalls, searing walls of energy at the event horizon that scramble information but don't destroy it. Then there's the wild card, equals EPA, a conjecture that entangled particles might be connected by microscopic wormholes, weaving space-time itself into a quantum network that preserves information in ways we can't yet measure. Recent experiments are turning abstract math into testable science. Quantum computers are simulating black hole dynamics, while labs are crafting analog black holes using sound waves in superfluid helium. Even gravitational wave detectors might one day spot hints of soft hair in the ripples of merging black holes. What makes this paradox so thrilling isn't just the answer, it's what the journey reveals about reality itself. Whether through soft hair, firewalls, or some yet undiscovered twist, solving the information paradox could unearth the missing link between quantum mechanics and gravity, rewriting physics in ways we can't yet imagine. Until then, black holes remain the universe's ultimate vaults, locking away secrets they refuse to surrender without a fight. The moon hangs in our sky as a silent, cratered companion, but beneath its dusty surface lies a puzzle that rewrites the story of its fiery youth. Today, the moon has no global magnetic field, yet ancient rocks brought back by Apollo astronauts bear the unmistakable fingerprints of one. These lunar samples, some over 3 billion years old, contain minerals magnetized in ways that only make sense if they cooled in the presence of a magnetic field as strong as Earth. How could this barren world, with a core just 1% of its mass, have once generated such a powerful magnetic shield? The answer lies in a turbulent past we're only beginning to unravel. For decades, scientists assumed the moon's small iron core couldn't sustain the convective churning needed to power a magnetic dynamo, the same process that generates Earth's protective field. Then came the Apollo samples. Tiny glass beads and basalt rocks showed magnetic imprints dating back to between 4.2 and 3.5 billion years ago, evidence that the moon's field lasted at least 1 billion years before fading into silence. This wasn't some faint whisper of magnetism. At its peak, the lunar field may have rivaled Earth's, defying everything we thought we knew about how planetary dynamos work. The leading theory, a celestial power boost from Earth itself. Early in the moon's history, its orbit was far closer, and Earth's gravity would have stretched and kneaded its molten interior like cosmic taffy. This tidal heating, combined with radioactive elements decaying in the core, could have supercharged convection, creating a temporary dynamo despite the moon's modest size. Think of it like spinning a penny in a bowl. With enough outside energy, even a small object can generate surprising motion. But the plot thickens. Some younger rocks, just 1 billion years old, show weak magnetic signatures too. If the moon's core had already cooled by then, what could explain these late flickers? One provocative idea points to colossal impacts. When asteroid strikes melted huge sections of the lunar crust, the swirling molten rock might have generated short-lived magnetic fields as it cooled. like spinning a magnet in a vat of molten iron. The Imbrium Basin, one of the Moon's largest impact scars, coincides roughly with this era, hinting that celestial violence could mimic a dynamo's effects. The implications reach far beyond lunar geology. If something as small as the Moon could sustain a strong magnetic field, exoplanets we've written off as too small might harbor protective shields, and with them, better odds for life. Meanwhile, NASA's upcoming Artemis missions aim to drill fresh core samples, hunting for clues in previously unexplored regions. Each new rock could rewrite the story of how worlds stay alive and why some, like our Moon, eventually go quiet. What began as a paradox in Apollo-era lab trays now stands as a testament to the Moon's lost dynamism, a reminder that even the most familiar worlds can hide explosive pasts beneath their tranquil surfaces. Hidden in the vast cosmic web where galaxies cluster like beads on invisible strings, lies a structure so enormous it shouldn't exist, the Hercules Corona Borealis Great Wall. This mind-bending filament of galaxies stretches an almost incomprehensible 10 billion light-years across, making it the single largest known structure in the observable universe. To put that in perspective, if you could travel at the speed of light, it would take you twice the age of Earth just to cross from one end to the other. Its discovery in 2013 didn't just break records, it shattered the theoretical limits of how big cosmic structures can grow. The Great Wall challenges a fundamental rule in cosmology called the cosmological principle, which states that, on large scales, the universe should look roughly the same in every direction. Structures like galaxy clusters or superclusters are expected, but something this colossal, it's like finding a single mountain range spanning half the planet. Astronomers first spotted it by mapping gamma-ray bursts, the universe's most violent explosions, which act like cosmic breadcrumbs tracing the distribution of matter. Instead of scattered randomly, these bursts revealed a dense, ribbon-like concentration of galaxies, all gravitationally bound in a single, staggering formation. What makes this wall even stranger is its timing. It existed when the universe was just 3 to 4 billion years old, far too early for gravity to have sculpted something so vast under standard models. Normally, structures this size take tens of billions of years to form, as matter gradually clumps together under its own pull. The Hercules Corona Borealis wall defies that timeline, as if the universe cheated its own physics to build a skyscraper overnight. Could this mean our understanding of dark matter, the invisible glue holding cosmic structures together, is flawed? Some theorists suggest exotic forms of dark matter with stronger clustering properties might explain it. Others propose the wall isn't a single structure but a chance alignment of smaller filaments, though the odds of such a perfect coincidence are slim. Then there's the radical idea that we're seeing a relic of inflation, the universe's explosive infancy when quantum fluctuations were stretched to unimaginable scales. Despite its grandeur, the Great Wall is invisible to ordinary telescopes. Its galaxies are so ancient and distant that their light has redshifted into near nothingness. Only by studying gamma-ray bursts, the universe's flashbulbs, can we trace its outline. New missions like the James Webb Space Telescope are now peering deeper into this cosmic frontier, searching for faint stellar fingerprints that might reveal how such a colossal thing came to be. The Hercules Corona Borealis Great Wall isn't just a curiosity, it's a cosmic rebellion, a structure so immense it forces us to question whether the universe plays by the rules we've written. And if this wall exists, what else lurks in the darkness, waiting to redefine the limits of reality itself? Mars has a gas problem, and it's one that could rewrite the story of life beyond Earth. For years, NASA Curiosity rover has sniffed out sporadic bursts of methane in Gale Crater, spikes where concentrations of the gas soar to 10 times background levels before vanishing just as suddenly. On Earth, 95% of methane comes from living things, cows, microbes, decaying plants, so these Martian whiffs have set off a firestorm of debate. Is this the long-awaited signature of alien microbes beneath the rust-colored soil? Or is the red planet just burping inert gas from ancient geological processes? The answer could hinge on a single, maddeningly simple molecule, and the race to decode its origins is tearing apart textbook assumptions about our planetary neighbor. What makes methane so intriguing isn't just its biological potential, it's the way it behaves. Unlike heavier gases that linger, methane is fragile, broken apart by ultraviolet light in just a few hundred years. Any methane detected today must have been released recently or be actively replenished. Curiosity's tunable laser spectrometer first caught whispers of it in 2013, with levels spiking unpredictably, sometimes vanishing within weeks. The most dramatic surge came in 2019, when methane concentrations rocketed to 21 parts per billion, the highest ever recorded. Yet when ESA's Trace Gas Orbiter scanned the same region from orbit, it found nothing. This mismatch isn't just frustrating, it suggests the methane is appearing and disappearing faster than our instruments can explain. Geologists point to abiotic sources like serpentinization, a reaction between water, carbon dioxide, and olivine rock that produces methane deep underground. Mars's volcanic past could have left pockets of this gas trapped in ice or minerals, slowly leaking through cracks. Another contender is photolysis. Ultraviolet light hitting meteorite delivered organic compounds on the surface, freeing methane in ephemeral puffs. These explanations fit the data, but they don't fully account for the erratic spikes. If the gas were purely geological, shouldn't it follow seasonal patterns like the ebb and flow of underground thawing? Then there's the biological angle. On Earth, methanogens microbes thriving without oxygen churn out methane in places like hydrothermal vents and peat bogs. Mars's subsurface, shielded from radiation and possibly warmed by geothermal heat, could host similar extremophiles. The methane spikes coincide roughly with warmer seasons, when hypothetical microbial communities might become more active. But proving this would require ruling out all non-living sources, a near impossible task from millions of miles away. The plot twisted further in 2021, when Curiosity detected organic salts alongside methane compounds that could be remnants of past life or just more abiotic chemistry. Meanwhile, experiments simulating Martian soil show that UV-exposed perchlorates might generate methane abiotically, muddying the waters even further. The truth might lie in isotopes. Methane from living things tends to pack lighter carbon atoms. If future rovers or sample return missions could weigh Martian methane's carbon fingerprint, it might finally settle the debate unless, of course, Mars has evolved its own unique rules. For now, the methane mystery remains a tantalizing cliffhanger. Perseverance, Curiosity's younger sibling, carries instruments to correlate methane with other gases, hunting for patterns that could trace its origin. ESA's Rosalind Franklin rover, set to launch in 2028, will drill 2 meters down deeper than any previous mission to sample soil untouched by surface radiation. Until then, each new whiff of methane keeps the question burning. Is Mars sighing with geology or whispering with life? The answer, whatever it is, will force us to rethink not just the red planet, but the very boundaries of what makes a world alive. At Saturn's North Pole, a storm rages unlike anything else in the solar system, not a swirling vortex or a chaotic tempest, but a near-perfect hexagon wider than 2 Earths stacked side by side. This 6-sided behemoth has churned in the planet's atmosphere for at least 40 years, possibly much longer, its razor-straight edges defying every expectation of how fluids behave. Hurricanes on Earth twist into spirals. Jupiter's Great Red Spot is a roiling oval, but Saturn's hexagon, it's a geometric enigma, a shape more at home in a honeycomb than a hydrogen-helium sky. The hexagon was first spotted in the 1980s by NASA's Voyager missions, but it wasn't until Cassini arrived in 2004 that scientists grasped its staggering precision. Each side spans nearly 9,000 miles, and the entire structure rotates with a period of about 10 hours and 39 minutes, matching Saturn's deep internal rotation, as if the planet's hidden heartbeat keeps time for this atmospheric ballet. Winds along the edges scream at over 200 miles per hour, yet the hexagon holds its shape with eerie stability, untroubled by the chaos around it. So how does a gas giant grow a polygon? The leading theory points to something called beta drift, a phenomenon where rapidly moving fluids like Saturn's jet streams can create standing waves that lock into geometric patterns. Imagine spinning a cup of coffee. The liquid forms a parabolic curve as it climbs the sides. Now scale that up to planetary dimensions, add layers of differentially rotating atmosphere, and you might get a wave trapped in a six-sided loop. Laboratory experiments with spinning fluids have even recreated crude hexagons, suggesting the shape emerges naturally under extreme conditions. But Saturn's version is far more precise and enduring than anything we've simulated, hinting at gaps in our understanding of fluid dynamics. Earth has nothing like it, and the reasons are written in the differences between our worlds. Saturn lacks solid continents or mountain ranges to disrupt atmospheric flow, allowing patterns to persist for centuries. Its deeper, faster jet streams powered by internal heat create conditions ripe for large-scale stability. Even Jupiter, despite its own turbulent storms, can't muster such geometric perfection. The hexagon seems to be Saturn's unique fingerprint, a product of its particular brew of spin, depth, and composition. Yet mysteries linger. Why 6 sides? Mathematical models suggest the number depends on the speed and depth of the jet stream, but no one knows why Saturn settled on this specific symmetry. Even stranger, the hexagon isn't static. Its color changes with Saturn's seasons, shifting from golden to blue as sunlight waxes and wanes over its 30-year orbit. Recent infrared observations reveal towering walls of layered haze inside the structure, stacked like a cosmic wedding cake, with temperatures plunging hundreds of degrees at higher altitudes. Perhaps the most haunting question isn't how the hexagon formed, but why it hasn't dissolved. Storms on gas planets are supposed to be transient, yet Saturn's North Pole wears this shape like a permanent tattoo. Some researchers speculate deep-seated magnetic fields or hidden vortices act as anchors, stabilizing the pattern against the atmosphere's fury. Others wonder if we're seeing a resonance phenomenon, where multiple atmospheric waves sync up like gears in a celestial clock. As Cassini's final images of the hexagon fade into the archive, they leave behind more than just data. They're a testament to the universe's flair for turning physics into art. On a planet where the rules are written in swirling gas, Saturn's hexagon stands as a reminder. Even the wildest chaos can sometimes fold itself into order. In the grand tapestry of the cosmic microwave background, the afterglow of the Big Bang, most fluctuations are subtle, like ripples on a pond. But one anomaly stands out like a frozen scream: the Eridanus supervoid, a chilling expanse of space so vast and empty that it stretches a staggering billion light-years across. This isn't just a quiet corner of the universe, it's a cosmic freezer, a region so profoundly cold that it defies easy explanation. When astronomers first mapped it in 2004, the temperature drop in this void was sharper and deeper than any model predicted, as if something had siphoned away the universe's warmth on an unimaginable scale. What makes the Eridanus supervoid so unsettling isn't just its size. It's the way it warps our understanding of cosmic structure. Voids are common, but they're usually no larger than 100 million light-years, with matter gradually thinning toward the center. This one, it's a billion light-year abyss, a cosmic sinkhole so empty that its gravitational pull has subtly stretched the light passing through it, a phenomenon called the integrated Sachs-Wolf effect. Photons from the CMB lose energy as they traverse the void's weakened gravity, cooling the background radiation in its shadow. The problem: the cooling effect is too strong. The void's observed depth suggests it shouldn't exist under standard cosmology, yet there it sits, an icy thumbprint on the sky. Theories to explain it range from the speculative to the surreal. One camp argues for cosmic textures, defects in spacetime left over from the universe's infancy, like wrinkles in a frozen sheet. These textures could create gravitational wells that siphon matter away, leaving behind vast, cold bubbles. Others propose a collision with a parallel universe, a bruise from a long-ago encounter with another cosmos in the multiverse. It's a radical idea, but the math shows such an event could theoretically imprint a cold spot of exactly this scale. Then there's the statistical fluke argument. Maybe the supervoid is just a rare, but natural fluctuation in the otherwise smooth CMB, the odds less than 1 in 50. That's like rolling a die 100 times and never landing on 6, possible but improbable enough to raise eyebrows. Skeptics point out that the void's shape isn't perfectly spherical, hinting it might be a chance overlap of smaller voids. Yet even this explanation feels strained, like fitting a square peg into a round hole. The true mystery lies in the void's silence. If it's truly empty, why hasn't surrounding matter flooded in to fill it? Some researchers speculate about dark energy acting locally, pushing matter away faster than gravity can pull it back. Others wonder if we're seeing the ghost of a primordial black hole, a relic so ancient it predates stars, its gravity long ago evacuating the region. For now, the Eridanus supervoid remains a cosmic Rorschach test, a blank spot that reveals as much about our theories as it does about the universe. Every new survey, from Planck's detailed CMB maps to next-generation telescopes like the LSST, brings us closer to an answer. Whether it's a flaw in our models, a window into the multiverse, or simply the universe trolling us with a statistical prank, one thing's certain. In the vast thermal hum of creation, this cold spot refuses to be ignored. The universe was supposed to follow rules, especially in its youth. Gas clouds should have clumped together chaotically, merging and colliding for billions of years before settling into orderly spiral disks like our Milky Way. But in 2020, astronomers staring 12.5 billion years into the past, just 1.5 billion years after the Big Bang, found something that shattered those expectations. There, glowing in the early cosmic dawn, was the Wolf Disk, a fully formed, rotating spiral galaxy, its elegant arms outstretched like a cosmic pinwheel. This wasn't just a little early, it was like finding a Renaissance masterpiece in a caveman's cave. The Wolf Disk, named after the late astronomer Arthur Wolf, defies every simulation of galaxy formation. At its discovery, it was already 10 times more massive than our Milky Way, with gas whirling around its center at speeds topping 170 miles per second. According to leading models, such a mature disk shouldn't have existed until at least 4 billion years after the Big Bang. Yet here it was, pristine and rotating smoothly in an era when the universe was still a cosmic toddler, brimming with turbulence. So how did this galactic prodigy form so quickly? One radical idea suggests cold gas accretion, a gentle rain of cosmic hydrogen flowing directly into the galaxy's core along dark matter filaments, bypassing the violent mergers that were thought to dominate the early universe. Picture a quiet stream filling a lake drop by drop, rather than a series of crashing tidal waves. Supporting this, ALMA telescope observations revealed the Wolf Disk's gas was unusually cold and stable, not the seething maelstrom expected in primordial galaxies. But the plot thickens. The Wolf Disk isn't alone. Other impossibly early disks, like the 10-billion-year-old galaxy ALMA 8111, show similar maturity. Even more baffling, some of these ancient disks host bars, dense linear structures of stars that typically take 8 billion years to develop, yet these galaxies sculpted them in under 3. It's as if the universe had a cheat code, accelerating galaxy growth in ways we've never accounted for. The implications ripple through cosmology. If disks formed this efficiently, our understanding of dark matter's role might need tweaking. perhaps its halos were smoother in the early universe, allowing gas to settle undisturbed. Or maybe magnetic fields, often overlooked in simulations, played a bigger part in shaping infant galaxies. Some theorists even speculate about top-down formation, where entire galactic disks condense directly from massive gas clouds, skipping the merger phase entirely. What makes these ancient disks more than cosmic curiosities is the way they force us to rethink time itself. The early universe wasn't just a rougher version of today's cosmos. It operated by different rules, or perhaps by rules we're only beginning to glimpse. With JWST now peering even further back in time, each new snapshot could reveal more of these impossible galaxies, quietly rewriting the story of how everything, including our own Milky Way, came to be. You'd think finding ordinary matter in the universe would be easy. After all, it makes up everything we can see, from stars to planets to our own bodies. But here's the cosmic kicker. Roughly half of this normal matter, called baryonic matter, has been missing for decades. It's not hiding as dark matter or some exotic particle. It's the same protons, neutrons, and electrons that build galaxies and coffee tables. The problem: these baryons are so diffuse, so fiendishly spread out across the universe's vast filaments, that they've eluded detection until now. This missing matter mystery began with the cosmic inventory. When scientists tallied up all the visible matter in galaxies, clusters, and gas clouds, it accounted for less than half of what the Big Bang's leftover radiation, the cosmic microwave background, said should be there. The numbers didn't add up. Where were the remaining baryons, the leading suspect, the cosmic web, the sprawling network of ultra-thin gas filaments that connects galaxies like threads in a spider's silk? These filaments, predicted by simulations, are so tenuous they're nearly invisible, their atoms too sparse to emit detectable light. The breakthrough came when astronomers realized they weren't just hunting gas, they were hunting heat. As the universe evolved, these filaments were theorized to absorb energy from stars and active galactic nuclei, warming to temperatures between 10,000 and 10 million degrees. At these extremes, the gas emits not visible light but faint X-rays. The challenge: capturing those whispers against the roaring background of the cosmos. Enter cutting-edge X-ray telescopes like ESA's XMM Newton and NASA Chandra, armed with spectrometers sensitive enough to tease out the fingerprints of highly ionized oxygen and nitrogen in these filaments. One pivotal discovery came from studying the galaxy cluster Able 2744. By mapping distortions in the cosmic microwave background as it passed through the cluster's surrounding gas, researchers detected a haze of warm, hot intergalactic medium, WIM for short, stretching far beyond the cluster's visible boundaries. This was the smoking gun, baryons hiding in plain sight, woven into the universe's scaffolding. Another clue emerged from fast radio bursts, those fleeting cosmic signals mentioned earlier. As these bursts travel through space, their waves slow slightly when passing through electrons in the WIM. By measuring this delay across multiple bursts, astronomers have begun charting the distribution of these elusive baryons in 3D. But the hunt isn't over. Some filaments remain stubbornly invisible, suggesting portions of the WIM might be even hotter or more diffuse than we thought. Others could be dark, their baryons locked in low-density molecular gases that don't emit X-rays at all. New tools like the upcoming Athena X-ray Observatory and the Simons Observatory's ground-based microwave arrays aim to close the gap, peering deeper into the cosmic web's shadows. What makes this search so thrilling isn't just ticking a box on the universe's balance sheet, it's about understanding how matter flows. These filaments aren't static, they're cosmic highways, funneling gas into galaxies and fueling star birth across billions of years. Solve the missing baryon puzzle, and we unlock secrets of how galaxies grow, why some regions of space teem with stars while others lie barren, and perhaps even how the universe's large-scale structure emerged from primordial chaos. For now, the cosmic web's hidden threads remind us that even the ordinary can be extraordinary when viewed at the scale of the cosmos. The universe didn't lose its baryons, it simply painted them in strokes too faint for us to see until now. And with every new detection, we're tracing the outlines of a masterpiece we're only beginning to comprehend. Black holes are cosmic sinkholes. Once anything crosses their event horizon, there's no escape. But what if the universe has a reset button? Enter white holes, the hypothetical opposites of black holes, where matter and energy erupt outward but nothing can enter. These bizarre cosmic fountains aren't just science fiction, they emerge from the same equations that predict black holes, simply running time backward. Imagine hitting rewind on a black hole's endless hunger. Instead of swallowing everything, it would violently expel it like a cosmic geyser locked in perpetual eruption. The math behind white holes comes straight from Einstein's general relativity. Flip the sign of time in a black hole solution and voila, you get a white hole. But while black holes are confirmed by everything from star orbits to gravitational waves, white holes remain purely theoretical. No telescope has ever caught one in the act. So why do physicists take them seriously? The answer lies in their potential role as bridges between two seemingly incompatible theories: general relativity and quantum mechanics. Loop quantum gravity, one of the leading approaches to unifying these two frameworks, suggests that at the tiniest scales, space-time isn't smooth but granular, a fabric woven from microscopic loops. When applied to black holes, this theory predicts something astonishing. As a black hole evaporates via Hawking radiation, it doesn't vanish. Instead, it could rebound as a white hole, spewing out all the information it once consumed. Picture a dying star collapsing into a black hole, only to bounce back like a rubber band stretched to its limit, transforming into a white hole in its final moments. The universe might even be hiding clues. Some gamma-ray bursts, the most energetic explosions known, have patterns that don't quite fit traditional supernova or neutron star collision models. In 2006, a burst named GRB 060614 flared with such intensity and duration that a handful of theorists wondered, could this be a white hole's birth cry? The idea remains fringe, but it's tantalizing. If white holes exist, they'd likely be short-lived, their explosive outbursts mimicking other cosmic cataclysms. The trick would be spotting signatures unique to a time-reversed event, like specific energy distributions or the absence of a progenitor star. Yet for all their elegance, white holes face glaring problems. Thermodynamics insists entropy always increases, yet a white hole's immaculate eruption seems to defy this by unmixing scrambled information. And if black holes can form naturally from collapsing stars, how would a white hole's initial condition, a singularity spontaneously bursting into existence, ever arise? Some theorists sidestep this by suggesting white holes only exist as endpoints for black hole decay, a cosmic recycling mechanism baked into quantum gravity. The most radical twist: white holes might not just be stellar-scale oddities. If the Big Bang was a white hole event, our entire universe could be the aftermath of some other cosmos's collapse. It's a dizzying thought, every galaxy, star, and planet riding the shockwave of a primordial rebound. Whether as cosmic mirages, quantum gravity's wildcards, or relics of a cyclic universe, white holes challenge us to rethink not just how space-time bends, but how it might, against all intuition, splash back. The universe has a birthday, an explosive beginning we call the Big Bang. But how does this cosmic story end? From the fiery collapse of a big crunch to the frozen silence of heat death, the fate of everything hinges on a single enigmatic force: dark energy. Right now, it's accelerating the universe's expansion, tearing galaxies apart faster than gravity can hold them together. But will this push ever weaken, reverse, or grow stronger? The answer lies in a tug of war we're only beginning to understand. Let's start with the bleakest scenario, heat death, also known as the Big Freeze. In this version of the end, dark energy keeps accelerating expansion indefinitely. Galaxies drift so far apart that their light can no longer reach one another. Stars burn out, black holes evaporate via Hawking radiation, and space itself cools to absolute zero. The universe becomes a vast, empty graveyard where even time loses meaning, a state physicists call maximum entropy. It's the ultimate equilibrium where energy is so evenly distributed that nothing can ever happen again. This fate seems likely if dark energy behaves like Einstein's cosmological constant, unchanging and eternal. But what if it's not so constant? Enter the Big Rip, a far more violent finale. If dark energy strengthens over time, its repulsive force could eventually overpower all binding forces, not just between galaxies but within them. First, galaxy clusters would tear apart. Then, individual stars would be ripped from their orbits. In the final moments, planets would disintegrate, atoms would be shredded, and space-time itself would fracture. The universe would end not with a whimper but a scream. This scenario hinges on a hypothetical form of dark energy called phantom energy, which grows denser as space expands. While unsettling, some models of quantum field theory allow for it, making the Big Rip a chilling possibility. But there's a third path, the Big Crunch. Imagine dark energy weakening or reversing, allowing gravity to claw everything back together. Billions of years from now, the universe's expansion could slow, halt, and then collapse in on itself. Galaxies would merge in a fiery chaos, temperatures would soar, and all matter would compress into a singularity, a mirror image of the Big Bang. Some cyclic universe theories suggest this could trigger a new Big Bang, birthing another cosmos in an endless loop. The catch: for a big crunch to happen, dark energy must be dynamic, perhaps decaying into something else over time. Current observations lean against this, but the universe has surprised us before. The wild card in all this, dark energy's true nature. Is it a fixed property of space, as the cosmological constant suggests, or is it a shifting field like quintessence that could fade or mutate? Experiments like the Dark Energy Survey and upcoming missions like Euclid are mapping billions of galaxies to trace how expansion has changed over cosmic history. Subtle variations could reveal whether we're headed for a freeze, a rip, or a rebirth. What makes this question so profound isn't just the scale, it's the stakes. The universe's fate isn't some abstract puzzle, it's the backdrop against which all existence plays out. Whether it ends in ice, fire, or rebirth, the answer rewrites not just our cosmic story, but our place within it. And with every new observation, we're not just passive witnesses to that story, we're detectives piecing together its final, breathtaking chapter. From rogue planets drifting in eternal darkness to quasars blazing with the energy of 1,000 galaxies, the universe constantly reminds us that reality is stranger than fiction. We've explored black holes leaking information, galaxies forming impossibly early, and cosmic voids so vast they defy physics, yet these are just fragments of the mysteries still lurking in the cosmos. For every answer science uncovers, a dozen new questions erupt, each more baffling than the last. Dark energy's relentless push, the Great Attractor's invisible pull, the whispers of potential life in Martian methane, each one proves how much we've yet to learn. This isn't just about filling gaps in textbooks. It's about confronting the humbling truth that the universe operates on scales and rules we're only beginning to grasp. The WOW signal's eerie silence, Oumuamua's cryptic acceleration, the hexagon storm on Saturn, none of these fit neatly into our models. They're cosmic puzzles begging us to rethink everything from gravity to the nature of time itself. And let's not forget the everyday enigmas. Why half the universe's matter is missing, why Tabby's star flickers like a broken bulb, or what truly lurks beyond the Kuiper cliff. Yet here's the beautiful part: every mystery is an invitation to peer deeper, question harder, and stay relentlessly curious. Maybe you're captivated by the chilling emptiness of the Boötes void, or the spine-tingling possibility of white holes erupting from dead black holes. Perhaps the Fermi paradox keeps you up at night, wondering if we're alone or if something out there is deliberately hiding. Whatever sparks your wonder, remember, the cosmos isn't just a place of answers. It's a frontier of endless discovery where even the weirdest phenomena are clues waiting to be deciphered. So tell us which of these cosmic riddles fascinates you the most. Drop it in the comments and don't forget to subscribe for more deep dives into the universe's greatest mysteries, because the adventure is just beginning and the next big revelation could be hiding in the next star system, the next dataset, or even the next flash of inspiration. Stay curious, keep looking up, and who knows, maybe one day you'll help unravel one of these enigmas yourself. The universe is waiting.